Hello and welcome back, everybody. For the next hour, we have two really interesting and experienced invited speakers who are going to talk to us. And don't forget, there's also a Slack channel for each of these talks. So please post questions in there so that we can get them answered. So our first speaker is Sreejit Chakraverty. He is a IEEE fellow and a distinguished engineer at Ampere Computing, where he drives the strategic initiatives for product quality. And prior, he was a principal engineer at Intel and a distinguished engineer at LSI and Avago. He's published a book, 150 to 200 articles, and holds 23 patents. We are extremely happy to welcome him to Hot Interconnects, where he's going to talk to us about the challenges and the ongoing efforts surrounding the test and repair of chiplet interconnects. So great, thank you.
Okay, can you guys see my desktop?
Yes.
Okay. Okay, good evening, folks, and good night to folks, maybe in other parts of the world. Let's see, how do I? Okay. So I'm going to talk about the chiplet interconnect test and repair problems. There is an effort to standardize it. And although it is not quite final, I'll highlight some of the ongoing effort. But more importantly, for this forum, most of you do not have the test background, manufacturing test background, and I'm assuming the viewership is mostly working at the architecture level. So my main goal would be to help you understand the definition of the problem, right? So that and then if I have time, I will add some of the gory details that go into actually standardizing it. Okay. Now, while going through the program, I found it difficult to find a talk or a title without the term AI in it. I mean, it is ubiquitous. Anywhere you go, AI is there. So this is my only AI slide in this presentation. Unfortunately, I'll have to apologize. I could not weave the word AI into the title or the discussion. So, I hope you'll forgive me for that. But I hope the rest of the topic would be interesting. Okay. So now that I've probably offended quite a few of you, and hopefully you are awake. Let's get to the subject matter. This is going to be the agenda for my talk. Okay. I will spend quite a bit of time in the first few items. And if I get through that, I will be very happy. Okay. And time permitting, I will get into the last few topics here. Okay. Which is really, the ongoing work. So let's start with the background. So, I wanted to provide two chiplet-based SoC examples. I was fortunate enough to work on both of them. They are a bit dated, but will illustrate an important point I'm trying to make. So the first one here is, is what is known as PVC or Ponte Vecchio. This is an HPC product, and Intel had put this on the market. I believe the follow-on is been now marketed, so this is probably off the market. The important thing to remember here is that there are a large number of chiplets referred to here as tiles, 47 of them that were integrated into this SoC. And more importantly, for our discussion, there are two types of packaging technologies that were used. One is, what is known as, at that time, Intel was calling it Foveros and EMIB. Okay, so keep this one of them in mind. The other product is Meteor Lake. And the Meteor Lake product is basically goes into the client. That means your laptops. And this also uses chiplet-based design. The number of chiplets here are much smaller. As you see from the figure, it is only 3, and it uses one packaging technology. Okay. The reason why I bring this up here is that there is a lot of discussion about chiplet around the very high performance computing products. Like, we talk about the monstrous AI chips that are being made. Yes, they are used there, but it is also used in other segments of the market. Okay, Meteor Lake is basically the client product, and they are also used in handheld devices, right? I also worked on a handheld device that was much smaller, much low power. So chiplet-based design is ubiquitous. It is, it permeates the entire spectrum of products. Okay, and what is important for us to understand here is that what can we do to, take it and facilitate this revolution that is upon us. So if you look at the current chiplet-based design methodology, okay, and and some of you can relate to that, every chiplet that goes into the SoC is being designed in-house. It could be by the same business unit, or there could be different business unit within the same company, organization. Now, there are a lot of cross-die features that needs to be defined and implemented, right? So currently, they're all defined and resolved in-house. Okay, and in addition to just defining the features, there is also the design support that is needed. So, either, if you're a large enough company, you can, develop your own homegrown tools. If you're not that large, you will go to a commercial tool vendor. But in this case, it has to be the same tool vendor, right? Now, standardizing solutions for cross-die issues is important in this context also. So even if two BUs are within the same organization, there is a lot of churn. Okay, I've experienced this myself. Okay, and once you standardize that, that takes a lot of discussion off the table. Okay, and you can add that, and that will definitely improves efficiency. Okay, and even from the tool perspective, if you standardize, since you can mix and match tools from various vendors, the cost also, the infrastructure cost goes down. So that's with the current state. Now, the CHIPS Act actually has envisioned something even beyond this, right? Essentially, we are looking at a marketplace of chiplets from multiple vendors. You could take a core from one, you could take the memory controller from one, you could take the accelerator from somebody else, okay? And then integrate it into an SoC. So we are really, envisioning a true Lego-like design, okay? And in order to actually fully exploit the benefit of chiplet-based designs, all using advanced packaging, all cross-die features really must be standardized, right? And the chiplet interconnect test and repair is one of those, right? Among the many that are that needs to be standardized. Okay, so that is really the motivation. Okay, so let's get back to the thing now. What do we mean really by chiplet interconnect test and the corresponding repair problem? Okay, so let's start drilling this down. If you look at the, I have a cartoon here, and this hierarchy, of interconnects that we can envision. So I envision it as architectural interface, followed, if you step down beyond that, it's the channel. Then we have the link layer, then we have the physical layer, and then we have the cluster layer, right? So let us try to understand what that is. So here is a cartoon of an SoC with 2 die, right? So, at the architecture level, what do we do? There is a lot of functional interfaces that we need to think about, right? I just put in a few examples, CHI interface, AIB, the CXL, VCIe. You could add your own favorite interfaces, okay? And then definitely when you design the SoC, you have to make sure that both dies support these architectural interfaces. What is less spoken about is what I refer to as infrastructure interfaces. They're also at the architectural level. So you have a whole lot of other interconnects. So for example, here we are talking about the SoC infrastructures. So there's, typically this includes a lot of reset signals, a lot of other handshaking signals across the die. For example, power good. Okay, it could also include security signals, things like that, right? Then you have the next bunch, which is for design for test. Okay, so at the end of the day, once you have assembled all of these, somehow the test stimuli has to be applied from an external source and special, and you need interconnects to transfer the test data, say in this case, into die 1 and die 2. And in the same vein, you have the debug buses. And then the last one that I show there is a test control, okay, which is a small number of wires that go across the SoCs in order to perform the test and control and configure the various dies into the test mode. So this is what we have, okay, and obviously die 1 and die 2 will be compatible if their architectural interfaces are compatible, right? Otherwise we cannot put them together. Now let's look at the next level. Once we get down, and this is, I just give you an example. This is true of pretty much any architectural interface. If you drill down one level down, then you'll see that there are two agents talking to each other on the die, and you have channels, right? I just put in an example of the CHI network. It is ARM's coherent hub interface. Okay, and you see that there are, typically depending on the agents, you'll have a couple of channels going from die 1 to die 2, and a couple of channels communicating back from die 2 to die 1. Now they have their own protocols, and the architectural protocols are built on top of that. Okay, so this is one level. Okay, and then if you go further down, okay, beneath each channel, what we have is the link layer. Okay, and below that is the physical layer. Okay, and below that is the clusters, right? So when we talk about the link layer, okay, we have a lot of different functions that are associated with the link layer: link initialization, credit management, power management, and RAS. And I've just put in a few of them. There is also this test, repair, and training that is done during the functional boot up process. Okay. Now, let's understand what we mean by clusters, okay, in the physical level. So if you look at further down, okay, if you look at a die-to-die chiplet interconnects, there are a very large number of them. I put in a number 200,000. I've worked with devices in that range, but you can imagine that as we are integrating more and more dies together, especially in these monstrous designs, this is increasing. So this is really large. Okay. Now, what are clusters? So we never design these interconnects to transfer data, okay, across the 200,000, right? So we never test them together. What happens is that cluster is nothing but a small collection of chiplet interconnects. And these are natural clustering that is imposed by the design. This is not a test requirement, right? And most of it comes from design requirements, because you have a clock, you have a data, there is a certain requirement for the skew between the clock and data. So unless and until a clock source controls a small number of interconnects, you cannot achieve that. Okay. And typically the way we do that is that, we go into a channel, it has 1,000 signals. We will break this down. okay? And they all work in the same clock domain, right? And we will break this down into smaller pieces. And the clusters are typically in the range of less than 50 signals per clusters, okay? And you have one clock associated with that. Okay, so if you look at this number and you assume that there are 100,000 interconnects, we are suddenly talking about a very large number of clusters. Okay, so training, repairing, and ensuring that all of these interconnects are working, okay, is time consuming and very tedious, right? And it has its own challenges. The other thing that you have to that I show here, which is important, is that each of these clusters are repaired, right? So if you think about having 50 signals and all 50 of them are not working, I add maybe 2 redundant interconnects, and then I reconfigure the cluster so that it uses 50 good ones. But the point is that I need to keep track of that repair and reconfiguration, right? So what is done is that once we have calculated the repair signature, as it is called, and I've been able to configure the cluster, then this has to be recorded in a permanent storage. Typically, it is a eFuse bank, and you have one such eFuse bank, okay, in each die. Okay, so this is what cluster level looks like. And the other point to remember is that every time you boot up the system, the repair signature from the eFuse has to be brought down to has to be downloaded into the cluster so that you're able to repair the cluster and power up. Okay, so keep that in mind. So this is the now. So what is high volume? Okay, all high volume manufacturing chiplet interconnect test and repair is very clustered oriented. Okay, now, so if you look at this figure again, okay, so we are not talking about doing the test and repair at the link level. We are really talking at a much lower level, okay, where we are going to use structural test. And these are not functional tests, okay, very targeted towards the kind of failure mechanisms that the interconnects will exhibit. And we have to know very specifically what kind of repair mechanism we are going to do, okay? And later on, we are going to see that in addition to what we do in high volume manufacturing, because before we ship out the SoC, we have to weed out the faulty SoCs so that our customers don't see it, okay? But once you have shipped it out, there are lingering challenges. And so we can also talk about extending this to the field, right? And that is what I refer to as infill extensions. Okay, so when we are talking, okay, so now let's look at what we mean by high volume manufacturing. Okay, so let's get back to this figure here. Okay, so when we start testing the entire SoC, we have to ensure before we do anything, right, that those interconnects are working. So at that point, very little of the die, each of these dies are up and working. So what needs to be functional at that? When I say functional, needs to have power maybe, okay, are only these clusters, right? These clusters are powered up, okay, and then the test control is powered up, and then the eFuse bank and its associated infrastructure is powered up, and some PLLs are running, right? Or we have the means to control the PLLs using the test control. That is all that is working. Everything else is non-functional. We don't even know if the rest of the die is working or not. So our first step is to test for these interconnects to work. Okay, and that is what is really the assumptions we make, and this is what we are referred to as the high volume manufacturing test and repair. So this is done at the lowest level. Okay. So a couple of things to remember is that when we are talking about structurally testing this, we are agnostic to the SoC's use of each of these interconnects. We don't care about what channel it belongs to. We don't care what architectural interface it belongs to. What is the purpose of this, whether it is a DFT signal or not, nothing. All that we are really interested in is that whether it is transferring the data from one die to the other at the rated speed. Okay. The only thing that we make a distinction between is that whether a channel is carrying a clock or a data. Okay. And we have to certify that each cluster transfer data across the die at the rated speed. Okay. And it utilizes the chiplet interconnect redundancy to repair clusters. And we require this to improve yield. Okay. That is the only reason. Okay. And then we'll also have to program the repair signature into the eFuse bank of each die. Okay. So that is really the high volume manufacturing test problem. Okay. When we are talking about standardizing, okay, we are really talking about standardizing the test and repair. So the initial goal of IEEE P3405 is to standardize that, but we are also considering that we will go ahead and standardize other aspects of it, namely the infill testing and the interconnect monitoring, because there is a big concern about reliability of these interconnects. Okay, so let's next move on to see, UCIe, there's a lot of noise and discussion about UCIe. We really need to understand what is the difference between UCIe and the IEEE P3400, right? The 3405. So as I mentioned, if I have a design without UCIe, okay, it'll look something like this. And P3405 sits inside is at the cluster level. Okay, and we talked about that. In case of UCIe, the way I look at it, UCIe is at the link layer, right? They are standardizing. There is a standardized UCIe link layer, and beyond that is the UCIe adaptation layer. And on top of that, we build all the architectural interfaces, right? Whether it is the PCIe or CXL or whatever it is. Okay, so this is, we have to keep this in mind. Okay, unlike the P3405, UCIe addresses the chiplet interconnect test and repair problem of the link layer. It assumes that the link layer is up and running, and if you think about it, in our terminology, link layer is actually part of the functional logic. Okay, so in our case, we cannot use this because we are assuming that the functional logic is not operational. So unlike the, just to stress the point, unlike the UCIe, the IEEE P3405 addresses the interconnect test and repair problem at the physical layer, and we assume none of the functional logic is up and running. Now, there is another point that, it's a bit subtle. It doesn't come through when you read the UCIe standard. Okay, there are a variety of interconnects that are used, and that depends on the product and the packaging type used. Okay, and our goal is to cover all those transmit receive types. Okay, and UCIe has some limitations. Okay, not that it cannot be changed, so future versions might modify it. Okay, but as so we don't want to distinguish between that, but we want to emphasize the point that we are trying to cover all products that use all different packaging types. Okay? And if time permits, I will talk a little more about that later on. Okay. Now let's see what UCIe entity looks like. So sorry, the P3405 entity looks like. So as I mentioned, the only thing that we are worried about is concerned about is that whether it carries data or clock. And a P3405 entity is the fundamental test and repair entity. That means we can independently test and repair that piece. Okay. Now, a cluster consists of one or more P3405 entity. I will explain to you later on with an example what do we mean by that. So we talked about cluster, but within the cluster, it can consist of multiple entities. Okay, and each entity is testable and repairable by itself. So there are really three types of entities that we talk about. One is just the data. That means all interconnects in this entity carry data, nothing else. Okay. Then there is a second kind, which we call clock. And what we see is that all entities in this cluster carry only clock. And then there is a mixed. Mixed means the interconnects in this entity can carry both a clock, either a clock or a data. Okay. And then if it is only a data type entity, then it has to be associated if it is a synchronous interconnect with a clock entity. Okay, but if it is carrying data asynchronously, then there is no need for that association. So it's difficult to, if you're not worked in this thing, it is difficult to understand this concept. It's a very simple concept. Okay, but let's see what happens, why we are doing that. So one of the things is that what we want to do is that if you are already using a certain link layer, let's say UCIe or some other link layer architectural protocol that already has the repair defined as part of that protocol, we don't want you to go back and change that as part of the IEEE 3405. We will say we will inherit that and we will use that. So we don't want additional hardware to be added. Okay. Now, the existing architectural functional interfaces that do not have test, repair, and training defined as part of it can leverage the new standard. Okay, and if we get this right, what I would go back and say is that anything new that you come up with, any architectural functional interfaces, don't worry about the test and repair part of it. We have already standardized it. Simply leverage it. Okay. And then there are a lot of architectural interfaces that are not standardized. For example, your DFT, your debug. Okay. Now, all of these, we say that you should go and leverage the new standard that we are developing. Okay. So if I look at inheritance backward compatibility, what we say is that either use P3405, inherit or leverage. Okay. Because there is the inheritance property. But for the rest of them that has no standard, no test and repair, directly use thing. So we will cover all these interfaces. All of these interfaces are important and we will cover all of them. Okay, I think this will help us understand, many of you understand the UCIe. And I've given you an example of the advanced package. So if you look at the left-hand side, drawn in pink, the UCIe has a class and advanced packaging. This is another name for what I am using the term cluster. Okay, it has a sideband and a main band component, right? And the sideband has a sideband clock with one redundancy. Sideband has a serial data with one redundancy. And similarly for the main band, we have clock, we have one redundancy. Then we have 32 data with two redundancy and so on, right? Now in P3405, we don't care. We don't distinguish between sideband and main band, right? All that we really care about is that, is this carrying clock, carrying data, or a mixture of the two? So the entity types that we will get from here is that it'll be a sideband clock. I'm just naming that. And it is a be of type clock. Similarly, it'll be sideband data. It'll be of type data. And you'll see the rest of the list. And that is an association, right? When I want to test the sideband data, I need it is a synchronous data transfer using the sideband clock. So we have to say that it is associated with sideband clock and so on. Okay. So in P3405, okay, we are going to test these entities independently. The only restriction is that if I have an association, like if I want to test the sideband data entity, then I need to make sure that the sideband clock is also tested. Okay, so I'm going to basically say that you have to first test and repair the sideband clock entity before you do the test the sideband data, and so on. Okay, I think I'm running out. Yeah.
Yeah, I wanted to let you know that we have hit time on this, and we were letting
Mm.
you go because our next speaker hadn't arrived yet, but now he's here. So I'll give you a couple minutes.
Okay. Sure. Okay. So let me then quickly go through this. I will just give you one example. Okay. Uh, So when we talk about some of the challenges there are two different kinds of drivers that we look at. Many of them look like the SerDes like which I show on the top, but many of them actually use the simple digital buffers. It's much simpler from our point of view. Okay, they are much better for test, and actually they are used in many of our products. So just to illustrate the point, if I look at if you look at how large is the market segment for products that simply use the simple buffers, it's actually pretty large. Okay, the numbers here will show you, in fact, for the Intel products, it is much larger than the DCI, which is the data center and AI product. For the AMD, it is not so large. If I throw in the NVIDIA products, it'll get skewed towards the SerDes. Okay, so that's one thing I wanted to mention. Okay, and the last thing that we can probably spend a little bit of time is that we have to understand what are the various defect types. So if you look at microbump, these are the various kinds of defects that we have to encounter, which include shorts and coupling. Okay, and when we go to the hybrid, okay, this is going to basically be a clustered open. Okay, I'm sorry, we ran out of time. Okay, but the last point I'll make is that if you come to the tutorial tomorrow, we'll get into the gory details. And the final thing that I'll mention here is that if you see the interconnects and you do a thermal map, okay, you will see that these are the hotspots in your design. And as a result of that, these interconnects will age very quickly. Okay, and so we need to start thinking about monitoring this and talking. Okay, so I think we can stop there and maybe have some time for a question or two.
All right, well, thank you very much. That was really interesting. You are absolutely right, not my area. I'm looking at the Slack and I don't see a question. I don't see any questions right now, but I'm going to encourage people to put something in there. I had a naive question for you, and that just had to do with redundancies. Are there really just one or two redundant interconnects in a cluster? And I guess that number was decided on by experience.
So
data on failure rates.
Yeah, so for every product, the way this goes is that for every the way I came up with this number is that for every product, you find out how many interconnects are there, and then you talk to your technology partner, whether in-house or externally, and there they will tell you what the failure rate is, right? Whether it is the 25 micron, 35 micron, or whatever, or further down. And then based on that, they say you need a certain level of repair. And that basically dictates how many repair you put in per cluster, right?
Okay.
Typically, 2 for every 30 is what currently is. But as we go further down, I think that needs to be increased. So,
okay, cool. All right.
Yeah.
That's what I was thinking. Let me do one last check of the All right, there are people typing. Let me give them 1 second here.
Okay, sure.
We are running behind. I do want to get Yuri on as soon as possible. All right. All right. I do have a question for you. So let me ask you this. This is from Sirkanth Gandhi, who asks, when you refer to repair of failed links, what does it entail?
Basically, you first have to decide where the redundant links are. That is decided a priori, and and then you put in a lot of multiplexing logic to take away one link, okay, and route the signal that is coming in was originally intended for that link to pass over a different link, a good link, right? And you cannot do that by just rerouting one of them. You might have to reroute a whole bunch of them, right? So yeah, a whole bunch of muxing logic. Yeah, I had a diagram somewhere, but we don't have time to go through that. But it's essentially muxing logic. Yeah.
Okay, great. Well, thank you.
Thank you.
And Sreejit, I'm gonna end your session here, and you might want to take a look at the Slack just in case someone asks one.
Okay.
Awesome. Well, thank you so much. That was super
Thank you.
interesting.